Hi everyone, my name is Darren Ramsook and I'll be presenting on a differentiable estimator of VMAP for video. This presentation is done for the Picture Coding Symposium 2021 conference. The presentation is organized as follows. First, we'll go through the introduction. Then we'll go through the problem of using still image models for video. Then we'll present our model. Then we'll go through the generation of our dataset, as well as training details, and finally results and conclusion. So perceptual visual quality metrics, or PVQMs, are thoroughly researched. And while they are actively used in post-hoc scenarios, such as assessing or testing the impact of a new compression or enhancement technique, they are not traditionally used in the loss function of that technique. And this could be attributed to the fact that most PVQMs are not readily differentiable, which means that the resulting nonlinear optimization strategy may be unstable. Throughout this presentation, we'll look at the applicability of estimating a differentiable complex PVQM. To do this, we use a convolutional neural network, and the PVQM under examination is the Video Multi-Method Assessment function, or the VMAP function. Now we move on to previous work. We know that there's existing work that proposes the use of a convolutional neural network to model a perceptual metric for still images. However, extending these models for use in video may be problematic due to the fact that these models do not capture temporal characteristics. We have also noted that neural networks has been formidable in creating perceptual features. And also pre-trained neural networks such as the VGG network has also been used to create perceptual scores for images. So now we're going to look at the problems in using still image models for video. On screen right now, you should see a video being played back. On the left panel, we have a raw uncompressed video, and on the right panel, we have the same video compressed with the HEVC video codec. So on the right panel, we should see blocking and other compression artifacts when referenced to the left panel. Now we're going to look at a 3-frame sequence extracted from the previous reference and degraded videos from the previous slide. For illustrative purposes, we're going to look at zoom patches over these frames at the same patch locations for the reference and degraded frames. So this is what figure 1 shows. In figure 1, the top row represents frames that are extracted from the reference video, while the second row represents frames extracted from the degraded video. Here we can see the effects of compression, such as blocking, and we could also see high noise content being decreased in the degraded video when compared to the original reference video. So now if we look at the VMAP score when considering no temporal motion, so that is each frame at each unique time index is compared to each other with no knowledge of the surrounding frames, we get scores 70.67, 56.25, and 50.32. However, when we consider motion, and that is the sequence of frames that process together, the resulting VMAP score is very different. To overcome the shortcomings of using the still image models for video, we propose a full reference differentiable estimate of a complex PVQM for video. So given the success of pre-trained deep convolutional neural networks for image tasks, we investigate both a fully trainable model with no shared weights and also a partially trainable model that exploits VGG. A convolutional neural network can facilitate a sequence of frames rather than a single frame as inputs, and this allows for the exploitation of temporal characteristics to be used when estimating the PVQM. We also look at the VGG model as the first layer of our proxy network, and this is done so that latent perceptual features learned by VGG can be easily exploited. So now look at the simple case of evaluating two frames from a video, F superscript R, which represents the reference video, and F superscript D, which represents the degraded video. The goal here is to create an easily differentiable function Q with parameters theta of an existing complex perceptual visual quality metric V. We can extend this idea to capture the temporal information by looking at frames around time index t. So in this case, we look at a 3-frame input over the degraded and reference frame, ranging from t-1 to t+1. So now we're going to look at the model architecture for the ProxVQM network. This is the fully trainable network. So starting from the left, we see we have two branches, one branch for the compressed input and one branch for the reference input. Each branch has 3 inputs, which corresponds to this 3-frame sequence for each of the compressed and reference video. Each frame is individually processed to extract spatial features, which are then concatenated with features extracted for each adjacent frame. These features are then processed to extract temporal features, and this is done on both the compressed and reference branch. These temporal features are then concatenated and further processed to generate a final score. Within each CNN block, there is a cascade of convolutional followed by Licurelu followed by max pool layers. The actual architecture for this network and also the other network that I'll be talking about can be found in our GitHub, which is also included in the reference in these slides. So now we look at the model architecture for the VGG ProxVQM network. On the left side, we have inputs corresponding to both the compressed and reference video. However, the first layer is now a section of the VGG network. The output from this layer is then fed into a convolutional neural network block. And this CNN block has its weights shared across each time indice and also across each compressed and reference branch. The outputs from this block is then concatenated and fed into a convolutional neural network block whose weights are shared across the compressed and reference branches. This network produces the temporal characteristics of the video and then concatenated and further processed to produce the final score. To generate data to train these models, we use the YouTube UGC 720p collection. One problem that can occur when generating data in this scenario is that it's possible for some quality scores to occur at a higher frequency than others. To overcome this, we compress clips using the H.265 codec with a CRF between 28 and 51. We then measure the distribution of the average VMAF score over a histogram bin of 10, and a certain number of clips were selected within each bin to create the final dataset. So this was done to create a uniform dataset over the VMAF range. Initially, we looked at varying values for the CRF factor, but we decided that 28 to 51 yielded the most uniform result. So this resulted in 13,178 3-frame sequences for training, and similarly 2,822 for validation and test sets. Here we have a histogram showing the count of frames over the VMAF range. So we could see that it's mostly uniform. However, there's still some bias towards the higher end of the range, particularly around 90 to 100 when compared to, for example, 0 to 10 on the VMAF range. For training, we use the mean squared error as the loss function. We also use the Adam optimizer with a learning rate of 1e minus 4 as the gradient optimizer. We also use spatial 2D dropouts with a probability of 0.2, and this allows us to simulate more data when training. Figure 5a and 5b both show the ProxVQM and VGG ProxVQM training graphs. The dotted green line in both of these figures correspond to the epoch number in which the loss for both training and validation loss were the lowest. From looking at these graphs, we could see that the VGG prox VQM converges at a lower training loss at an earlier epoch when compared to the prox VQM model. Here we have the results of our trained network. In figure 6a, we have the prox VQM network. The correlation coefficient is 0.982 and the rank correlation coefficient of 0.98. In the x-axis, we have the ground truth VMAF scores, and on the y-axis, we have the predicted VMAF scores. We can see a strong linear correlation. However, there is some deviation occurring, some spread occurring between the regions of 80 to 100 and also around 40 to 60. When looking at the VGG prox VQM network, which is figure 6b, we have better performance in the correlation coefficient as well as the rank correlation coefficient. And also, but however, they could see there's still some spread noticeably around the 20 to 40 VMAF range. After training, we could see that the VGG prox VQM has a lower RMSE of 4.41. Here we could see an example of the networks being used to predict the VMAF score over a sequence of 3 frames. In figure 7, the top row corresponds to the reference frames and the second row, F superscript D, corresponds to heavily degraded frames. In this example, the effects of degradation are very visible. Consequently, the associated ground truth VMAF score is very low, which is 16.31. Our both prox VQM and VGG prox VQM predictions came close. However, the VGG prox VQM predicted a score closer to the original ground truth. Here we have an example of using the networks to predict the VMAF score over a 3-frame sequence. The top row corresponds to the reference frames, while the bottom row corresponds to lightly degraded frames, which means a very high ground truth VMAF score. In both cases, our networks came close. However, again, the VGG prox VQM had a closer prediction to the original ground truth. In closing, we can make these final comments. We could say that there has been limited use of PVQMs for video enhancement, as they are generally complex and non-differentiable. We propose a convolutional neural network to approximate a popular perceptual visual quality metric, in this case VMAF, and we built on existing architectures to include the use of temporal characteristics of the metric. The YouTube UGC 720p collection was used for generating training data. The video was degraded using the H.2.5 codec by varying the CRF control. The VGG prox VQM network achieved a lower root mean squared error. And also in future, we'll be applying this linearized VMAF to perceptual video enhancement operations. In closing, I'd like to acknowledge the Science Foundation Ireland Centre for Research Training in Digitally Enhanced Reality and also YouTube. And here's a list of my references as well as my GitHub repo.